Hello. So we have considered the basic property, four important properties of sample mean y bar with respect to the population mean by. And simply speaking, two most important properties are these. The sample average converges in probability to the population mean as the sample size diverges to the infinity. And second, the standardized sample average is normally distributed, approximately standard normal distribution if the sample size is large enough, right? And standardization is subtracting the expected value and dividing by the standard deviation, square root of variance. Then after this standardization, the variance is normal 0, 1. So that's a nice property about y bar, the sample average, and it already proves two important desirable properties of y bar as an estimator. Here we have another. We are going to justify y bar in a different way. Now consider this problem. Instead of estimating, consider that we are predicting the value of y by a value m. So before looking at what happens, I am going to, before drawing the random number, we are going to predict the value. Then the error is, in this prediction, the error is the difference between y and m. Y minus m is the random error from the randomness, and this is called the residual. So you predict y by m, but some part of y is not explained, not predicted. So y minus m is called the unexplained part, the residual. And by the way, we have n number of observations, n number of realizations of y. So basically, you are predicting y n number of times. So there are n number of prediction errors. So for the ith observation, for each realization yi, your error is yi minus m. This is your prediction error when you use m, predictor m. By the way, this prediction error could be positive. The residual could be positive for some observations. In those cases, the prediction is underestimation, but others may have negative values, which is an overestimation, right? So there are positives and negatives. Both are bad. What you want is you want the error to be 0, but practically that's not possible. But anyhow, you want to make the errors as close to 0 as possible. The best predictor will reduce the error, the size of the error in both sides, from both directions, from the negative or from the positive. And what we do here is we would like to measure the total amount of the residuals by one number. But this being positive and being negative cause problem, because some positive random errors, when you simply sum those errors, positive random errors will cancel out the negative random errors. So in the end, it may be 0, even though there are many positive and negative errors. So to avoid those kind of cancel outs, we not simply sum them, but we sum their squared values. We sum them after taking squares. So mathematically, you can write it this way. yi minus m is your prediction error for ith observation, and square that. And for each I, you can calculate those squared errors and sum out those squared errors. Then it is called the sum of squared errors or the sum of squared residuals. This is a measure of the amount of the errors, the total size of the prediction errors or the residuals. So simply speaking, the smaller, the better. The smaller this sum of squared error is, the better and the more accurate your predictor is. So this is another approach to justify y bar. So then anyhow, think about this. But we have not defined what is the predictor. We have like the predictor, we just assume that once you have the predictor m, then you can follow these steps like whenever you have the data. Then mathematically, we may consider m that minimizes this sum of squared residuals, right? Sum of squared residuals can be minimized. So if you minimize, if you choose m that minimizes this sum, that is the best predictor. That minimizes the prediction errors, which is defined if the error is defined by this way, defined in this way. So that is the least squares approach. This is another way to justify the sample average. Previously, in our previous results, we already learned that the sample average is unbiased, which means the expected value of the sample average is the true parameter, or so your sample average is on average correct. Second, we learned that sample average is consistent, so that the sample average will be exactly the true parameter without any uncertainty in the end, in the limit. And the third justification you can consider is this way. We define the prediction errors, we measure the prediction errors in this way, and you minimize it. Then how can you minimize it without observing the data? Actually, you can. The minimization is is exactly what you did in microeconomics. Like differentiate and take the first of the condition, then you are going to get the minimum is achieved when m equals to y bar. So this calculation is first of the condition. It's not that difficult to show, but anyhow, the result is quite intuitive. The sample average minimizes this sum of squared errors. So we say at y bar, the sample average is the least squares estimator, minimizing the sum of squared errors. So least squares or LS estimator is from this idea. So as a result, you can say that y bar has a smaller variance than any other unbiased estimators. So for example, what this means is that think about any other weighted averages. So any other weighted average means you are not simply sum and divide by n, but you put some kind of weights. So even if like I don't know what these weights are, but it doesn't matter. No matter what you weight, your estimator will be worse than y bar in terms of their variances. So the variance is the uncertainty of your estimator, or how inaccurate your estimator are. It's because it's about the spread divergence from the true parameter. So the smaller the variance, the better, right? The estimator is. And mathematically, you can show that your estimator calculated by this method will achieve the minimum variance among other comparable linear unbiased estimators with special weights. So weights are not improving anything. That's the mathematical result. So by the way, however, it doesn't say y bar is always the best. Later on, we need to consider alternative estimators, but in most cases, in many cases, the sample average is the best estimator for the population mean. And we already use the sample average in many applications and many just in our daily life. So already the use of the sample average is justified by many statistical theories. However, it is not the only estimator. Understand it. You need to understand it too. So, for example, median could be an alternative estimator for the population mean, but that's not considered for a while. Based on these theoretical justifications, we are going to rely on the sample average. Okay, in the next slide, so I have explained the basic theories in the estimation and the sampling distribution and the desirable properties of estimators and why the sample average is the best estimator for the population mean. And from the next video, we are heading into the hypothesis testing chapter, which must be the most challenging part so far. So hypothesis testing has a much more complicated structure than estimation and other statistic theory. So get ready for that. See you in the next video.